In this video, we're going to cover some astronomy basics. We'll talk about the life cycle of a star. We'll go over a binary star system. We'll talk more about the gravitational force and how to use that formula. We'll go over the momentum principle again quickly, and then we'll also talk about the system and surroundings again quickly. And we will hopefully apply this information successfully to a problem here that has to do with the binary star system. So starting with astronomy is just a branch of science that deals with celestial objects and the physical universe as a whole. And we all know probably what a planet is. It's just a celestial body moving in an elliptical orbit around a star. In our case, our star is our sun. And we have our solar system here with the sun, and we have Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune, and so on. We have trans-Neptunian planets as well. And we exist within the Milky Way galaxy, but there's other galaxies as well. It's a system of millions or billions of stars together with gas and dust held together with gravitational attraction. So we have a galaxy, which is kind of one step farther, zooming out. And then we have the entire universe as well, including the visible and the invisible universe. It's basically just all the collection of all things that exist in space. It's the idea of a universe. And so within this we also have comets, which are just basically ice and dust collections that orbit a star like our sun. We have asteroids, which are very similar, but they're small rocky bodies. We have the asteroid belt here, which is a region between Mars and Jupiter. We have meteoroids, and so sometimes an asteroid can smash into another one. Then you get small pieces that break off, and so here's the asteroid. You get a small piece that breaks off called a meteoroid. And then we have a meteor if it enters Earth's atmosphere and it vaporizes. And we also have meteorites, and so sometimes they don't vaporize completely, and they survive that trip, and they land on Earth's surface, and so we call them meteorites here on Earth. And so getting into the life cycle of a star, we have a nebula here, which is basically just a cloud of gas and dust in outer space. And we have stars that start to form. We call them protostars, and it's gathering mass from its parent molecular cloud. We have most of the stars in our universe are main sequence stars, and so we have nuclear fusion, which is converting hydrogen into helium, and that's creating a whole bunch of outward heat and pressure, which is basically resisting the collapse from gravity, acting the other way. And so we also have these red giants or supergiants. There's kind of two pathways. One's a low or medium mass, and one's a high mass. And so these are basically dying stars, and they're running out of hydrogen fuel. And so that heat and pressure is dying down or running out of fuel. We have a supernova that could potentially occur, which is a sudden increase in brightness and this catastrophic explosion that ejects most of its mass. We have a planetary nebula that could also happen. And so from that, today we'll kind of have an example of a white dwarf, and so that's basically just after this planetary nebula we have a dense star that's typically the size of a planet, and then we also have a black dwarf after that. So basically once it's cooled significantly, it's not really emitting much light, and it becomes a black dwarf. And then over here after the supernova we could have a neutron star, which is pretty much one of the densest stars that you can have. It's the collapsed core of a giant star. And then we also could have a black hole, which I'm sure you've heard of. And that's basically a region where the gravitational field is so intense that you can't have matter or radiation escape like light. All right, so now we'll go into a binary star system. And so a binary star system, we have two stars here, bi meaning two, and they're orbiting around a barycenter or center of mass. The gravitational pull between them causes them to orbit around that center of mass. And the reason why these are important is they're relatively common, and we can use them to determine the mass of a star by looking at their orbits. And as you can imagine, it's quite difficult to measure the mass of an entire planet or star, right? So we have to use other means of doing it. The binary star system in this problem that we're going to do today, it resembles a real one. You would think that the northern star might be the brightest one, but it's not. So the brightest star visible from Earth is Sirius, and we have Sirius A and B, and the B is the white dwarf companion, and so they orbit each other with a period of about 50 years, and so the one that we'll do today kind of resembles that. And so we'll go over force just briefly. Again, the main one that we have to focus on, remember, force is any interaction that when unopposed will change the motion of an object. We have those 4 fundamental forces. We got the Newton's 3 laws of motion, which is really talking about forces. And we have friction, we got electromagnetic, we got buoyancy, centripetal force, spring force, but really we got to get more detailed on gravity here. So we know that the weight of an object, or force of gravity, is mg, and so this g can actually be just kind of magnified to look at that a little bit deeper. And we look at a situation like this where we have those two masses attracting each other. And we have mass 1 and mass 2, and so we have this big G, the gravitational constant, times the mass of the first object, mass of the second object, over their distance of separation squared. And then we have a unit vector to give direction, and this unit vector coupled with the negative sign just basically is indicating that it's an attractive force. And so this formula gets sometimes confused, and the notation is kind of tricky, so I tried to label it here with red and blue. And the general idea here is that if you notice, the position vector is in the opposite direction. And so the blues, you can see how they're pointed opposite, and the reds, you can see how they're pointed opposite. And so that's the general idea. And that's because it's an attractive force. And so the force is going to be in the opposite direction of the unit vector based on how this is defined. And in order to find that unit vector, we can use this formula here, which is basically just subtracting the two position vectors here and then dividing by that magnitude. And so also one thing to note is that this entire thing here, which we'll see today, can be just viewed as the magnitude of the gravitational force, and then remember that negative in that unit vector can give it the direction. And then another thing to note again is just that the one unit vector is just the opposite of the other one, and same thing with the force, and so they're basically equal in magnitude but opposite direction. And so that's an important thing to keep in mind with this formula that we're going to use today. Alrighty, so momentum and impulse we should be familiar with by now, but momentum is basically mass times velocity. We should know that it's a vector. Same thing with impulse anytime you have a change in momentum. And so we're going to assume a lot of times that the net force or acceleration is constant, or we have small enough time intervals to do some approximations. And so we're going to potentially be using these updates, which is an iterative process. We have this momentum update, which we've talked about, and this momentum principle, which is basically just Newton's second law, and Newton's second law connecting it to momentum. And then from that, position update can arise here. And so we can take the momentum principle and kind of use it to update our position. And we can actually make an additional approximation here with the variable force a lot of times, where we can just say that the average velocity is the final velocity. And so those formulas here that are boxed are fairly important for us. And so we also have to talk about the system and surroundings. And so the system, remember, is just anything that is forming a complex whole. It has a bunch of parts to it, and you can set it to be whatever you want. And then the surroundings or environment is everything outside of the system. And so we can potentially have energy and matter transfer between them. We also can look at an object, and we can look at as our system, and we can look at the forces acting on that system. We have 3 basic types of systems that we like to talk about. Isolated systems are often ideal because then you don't have to consider the surroundings, but a lot of times we don't want that. We actually do want to consider the surroundings, and so we'll see that today play out with picking different systems and surroundings, but that's the general idea. And so today we're really talking about momentum and how momentum can change. And so if the momentum changes in a system, it must have gone to the surroundings and vice versa. And so it's this idea that basically the change of momentum of the system is equal to the negative change of momentum of the surroundings. In other words, you add them together and you get 0. And so we can talk about Also, if we look at this, these little particles in our system, we could potentially have some internal forces happening in our system, but all of that stuff is basically going to cancel out. And so the change in momentum of our system is really only dependent on any net forces from the surroundings times the change in time. And so if we have an isolated system, remember an isolated system has no significant interactions with the surroundings, then we're going to have 0 Newton seconds of our change of momentum. There is not going to be any change of momentum of our system if we have an isolated system. Okay, so now let's get into our problem. And so with this problem, we have a binary star system, and we have our A and B stars, and they give us the masses, they give us the initial positions and velocities, and they give us that magnitude of the gravitational force. So we actually don't have to do the g m1 m2 over r squared. They're basically just giving us that magnitude of that gravitational attraction. And so what we need to do for part 1 is find the initial momentum of this binary star system, and we need to estimate the system's momentum 1 week later. And remember, if from the earlier slide, we know that this resembles a real binary star system called Sirius, and it has a period of about 50 years. And so 1 week later is really not that significant if you think about 50 years it takes. And so we're going to first kind of draw a diagram here, and so we can kind of illustrate the different forces that are happening. And so we clearly have some velocity, which is kind of like tangential to the orbit, but then the forces are kind of right along that line that goes through the center of mass. And so they're clearly interacting with each other, and they're exhibiting equal forces on each other, but opposite directions. And so we can set the system, actually, in this case, to be both stars, because they want to estimate the system's momentum a week later, and they're talking about the whole system as a whole. And so the surroundings in this case would be nothing significant. We can kind of assume that it's isolated and no other stars or planets or whatever are nearby enough to affect it. And so obviously that's a pretty big assumption, but we're going to use the momentum principle, and we'll look at that formula that we talked about earlier along with the idea of momentum conservation. And since this two-star system is far away from other objects, like I said, we can neglect those effects for simplicity, and then we can also assume that the speed of these are pretty small, so we can approximate that the gamma is about 1, which means there's no relativistic effects. It's very, very slow compared to the speed of light. And so what we'll do is we'll solve the problem. And so what we need to do is, since we know the masses and the initial velocities, we can talk about the momentum. And so we look at this formula, which I had over here pretty much. And so we know that the change in momentum of the system is actually 0. And that's because, remember, we defined our surroundings to pretty much be nothing significant. And remember, the change of momentum of the system only depends on the net force from the surroundings. And so if we have the system being both stars, the surroundings is basically 0. And so we have an isolated system, so that the change in momentum of our system is 0. And so what that means is that we can basically just look at what our initial momentum is, and we know that our initial momentum then is pretty much going to be equal to our final momentum, because there was no change. And so remember, the change is final minus initial. And so if the final and initial are the same, it's going to be 0. And so what we can do then is just basically approximate that the initial momentum of our system is equal to both of those momentums added together. And so we'll take the momentum of star A and we'll add it together with the momentum of star B. And once we add those together, we get this initial momentum of our system of about 6, 0, 0. And it looks like the other dimensions cancel out, times 10 to the 34 kilogram meter per second. And so that ends up being the initial and final 1 week later, because of how we defined our system. Okay, so now part 2, it'll be a little bit more messy. We're basically looking at just star B as our system, and so in that case the surroundings would be star A in terms of what's significant. And so the force on star B by star A is assumed to be about constant for about that week, because in the period of 50 years, 1 week is not that much. And so even though these distances might be changing, we can kind of assume that the force is not going to be changing significantly for us to have to recalculate it. And so also we can assume that there's no other significant interactions from the surroundings other than star A, and we can again assume that the speed is small enough to avoid relativistic effects. And so what we can do then is, from part 1, we know our initial momentum of star B. We basically just plug in the mass of star B times the initial velocity of star B, and so now we have our initial momentum of star B. And so we want to figure out, it says what is the initial momentum of star B, so we got that. And it says also estimate the change in its momentum during the following week later. So what's it going to be a week later? And so what we need to do first is kind of look at the unit vector and the force here. And so before we didn't really have any net force from our surroundings, and now we do. And so we only have the magnitude of the gravitational force. We need the direction as well. And so what we do then is we'll find that unit vector, and we'll find the unit vector of star B relative to A. We can call that RBA, and that's kind of pointed at star B. And we know that the force is going to be opposite that, and so that's kind of shown here in this formula graphic that I showed you earlier. But we know these positions, and so what we'll do is we'll just subtract the positions that they give us and divide by the magnitude. And what we'll do there, notice how with the magnitude we're basically doing the Pythagorean theorem. And so once we do that, we'll have our unit vector, and notice how that's positive, comma, positive, so it's kind of up and to the right. But we know our force is down and to the left, and so what we need to do then is negate it. And so we'll take our unit vector and negate it, and that'll give us the direction of our force. And so we'll take the negative of the unit vector, and that's very important. Then we'll multiply that negative unit vector by the magnitude that they give us, and that will give us the full vector force that we need, including its direction. And so now that that's done, that's kind of the hard part. Now we can just apply that momentum principle 1 week later, but recall that we kind of need to convert to seconds, because something like impulse is measured in like Newton seconds, and so a lot of times we have to convert to seconds. And so 1 week, we have to multiply that by 7 days in a week, 24 hours in a day, 60 minutes in an hour, 60 seconds in a minute, and we end up getting the amount of seconds here in 1 week. And so then what we can do is plug that in for our time. We have our change of momentum is that force times the time, and so we take our force that we just found up here and we multiply it by our time in seconds, and then we have our change of momentum over that week time period on star B, because star B is our system. And so I'd also ask for the corresponding change in velocity, and so what we can do there is basically just divide by the mass. And so if we look, the mass of star B is up here, 2 times 10 to the 30th. And so we'll basically just divide by that, and we can get the corresponding change in velocity during that time. And you notice how it's really not that much. And so we have negative 0.43 and then negative 0.575. And so it kind of makes sense because it's only a week. And it's, remember, a period of 50 years. So there shouldn't be that much change in velocity. And so they are small compared to the components of its initial velocity, so it's reasonable to estimate that the displacement of star B in 1 week is really not that much. And so what we can do is just say that the initial velocity of star B is approximately equal to the average, which is approximately equal to the final. And so what we could then do is kind of look at the change in position if we wanted to, and say that the change in position is equal to the velocity times the time. And we could plug in our velocity up here, and we could find the change in position as well. And so we'll move on to this next part here. Just remember that that we are basically assuming that these components are really small changes, and so it really doesn't change significantly in 1 week. The force changes, and so that means our estimate of the change in momentum of star B is pretty accurate. And so we'll look at part 3, And so we'll just basically do the opposite of what we did. It's just kind of an extension of part 2. And so now we'll set our system to be star A and our surroundings to be star B. And so again, we'll make our similar assumptions, and we will get on to the business here. And so in this case, we kind of have the opposite effect here, where our unit vector is going to be, again, in the opposite direction of the force, but we're considering our system to be the star A and not star B. And so one thing we can do, though, is basically just use the reciprocity idea, and we can say that, well, we calculated the initial momentum in part 1, so that's what we can start with. But we then can kind of take a shortcut and say that the change of momentum of A is just going to be the negative change of B. And so we can just, plug in our, whatever we got for B and then just negate it. And that just really saves us a lot of work. And so the only issue then is, because the masses are different, just because the changes in momentum are pretty much equal but opposite, we also need to consider the masses, though, when we're talking about the change in velocity. And so the change in velocity of A is actually going to be negative but half the change in velocity of B. And so that's because if you look, the mass of A is twice as much as the mass of B. And so we have 4 times 10 to the 30th, and we have 2 times 10 to the 30th. And so when we work that out, we get a change in velocity of A to be this here in meters per second. And then remember that we could also find the change in position if we wanted to as well, just by multiplying the initial velocity of A times that time frame, and we could get our change in position. And so remember that they're pretty small values here again, and we're done. So I hope that this showed you some examples of how we can use physics with astronomy, and a little bit more on how to use that force formula, how to define our systems, how to use that momentum and position update. And so we will see you in the next one.